Hey guys, so today in this video, we're going to talk about the work done by a variable force acting on an object. So contrary to work done by a constant force, in cases where the force is not constant, we have to use calculus, specifically integration, to determine the work done by the force in question. So let's go ahead and take a look at a practice problem and what that process looks like. All right, so in this problem here, we have a force exerted on an object given by the equation F equals 4x squared minus 2x. So clearly a force that is not constant, it varies with respect to the object's position. And we want to calculate the work done by this force when the object is displaced 10 meters from its initial position. So let's go ahead and take a look here at the definition of work, and the work done is the integral of that force expression with respect to position, and we evaluate that from the initial position to the final position. So in this case, we have to know how to use the reverse power rule for integration in order to integrate this force function. So to do this, we are going to, let me go ahead and actually put those numbers in there. So we're going to go from the initial position of 0 meters to 10 meters and integrate this force function. So when we do this, like I mentioned, we're using the reverse power rule. So we need to here take that first term, 4x squared, and we're going to bump that exponent up from 2 to 3 and divide by the number that we just bumped our exponent up to. Okay, so we're going to do the same thing with the second term in our expression. So we're going to keep that subtraction sign there, and we're going to bump x up from, so we can imagine that x alone being x to the first power. So we're going to bump x up to the second power and divide by the number that we just bumped our exponent up to. Of course, this we can simplify a little bit, but we're going to evaluate that from the lower bound of 0 meters to the upper bound of 10. So let me just go ahead and rewrite this in its simplified form. So 4x cubed over 3, nothing really too much to simplify there. And then over here, I'll just simplify that to x squared. And so the first thing that we're going to do is evaluate that expression at 10 meters and subtract that expression evaluated at 0 meters. Okay, so we're going to just plug 10 in here, so that's 10 meters. And we're not even, guys, I'm not even going to bother. If we had a non-zero number here, we would subtract from this expression. This expression evaluated with that lower bound, but since it's 0, we can just leave that off. And so when we actually plug that in here, we come up with about 1,200 joules of work done. Okay, so clearly if I was rounding this to the appropriate number of significant figures based on what I'm giving here, I would only leave myself with 1, but I'm just going to round to 1,200 joules. All right, so just to summarize here, what our process was when we saw that our force was variable with respect to position, we decided that we were going to integrate that force function in order to find the work done. So in this example here, we use the reverse power rule of integration to determine what that expression should look like, and then we evaluated that expression at the upper bound, so that we see here. We evaluated it at the lower bound, but that of course was 0, and that led us to being able to find the work done by that force. Let's take a look at another example. All right, so in this problem here, we have a force exerted on a nonlinear spring, so one that does not obey Hooke's law. A force constant 150 newtons per meter is given by the equation F equals kx squared minus 2x. So k is that force constant. We want to determine the work done on the spring in stretching it 15 centimeters from its equilibrium position. All right, so our process here is going to again be along the same lines, where in order to find the work done, we need to integrate this force function with respect to position from an initial unstretched position, which would be 0 meters, to 15 centimeters or 0.15 meters. All right, guys, so I'm going to substitute in that force expression, and we're going to integrate across those bounds. So k x squared minus 2x dx. And I kind of glossed over this a little bit in the last problem, but since we have this k in there this time, let's just also make sure that we cover this idea of being able to say that if I take and split apart this integral, this means the same thing as what I have there above. Okay, so I can just split this apart here, integrate these terms separately, but as I'm subtracting here, I am subtracting here as well. All right, so in the first part of that, I can pull out k as a constant, right? And in here, I keep the x squared dx from 0 to 0.15. Subtracting, here I have the integral of 2x dx. And we have two pretty simple things going on here. So that constant, and when we take the antiderivative of x squared, again, we're going to bump x up to the power of 3 and divide by what we bumped our integral up to. And then for 2x, our antiderivative is x squared. So this time I'm just going to leave out where I divided by 2 because our 2's are going to cancel out. And then this expression here I can evaluate from 0 to 0.15 meters. Okay, so the work done, I'm going to go ahead and put that 150 newtons per meter in there for my constant. 0.15 meters cubed in there. Okay, we're dividing that by 3 minus 0.15 meters squared. And the work done in stretching that spring with that equation for the force exerted on it is equal to about 0.15 joules. And guys, that's kind of just a coincidence there, just FYI that we went to 0.15 meters, and that was also our answer there. But that's what we would come up with for the work done. So we have two examples there of using that reverse power rule for integration to determine the work done when we have a force that's changing with respect to position. Otherwise, if we have a force that's constant, it makes it a little bit easier on us because we can use the equation FR cosine theta. But remember, this equation here is only for those types of scenarios in which we have a constant force being exerted on that object. But for these two practice problems that we looked at today, that's just not the case. We had to integrate instead.